That's it.
Welcome. So this talk tonight is on a class I did from January to May 2015 called Embedded System Shape and Work. There'll be a lot of content mentioned, so I won't have time to go into much detail. A lot of these slides could be presentation on their own. Please ask questions during the presentation, and if you have better examples or comments, please put it in. So, when I was younger, I used to pull my toys apart to see how they worked. Apparently that's a sign you might be a future engineer. In high school, I did a class called Information Processing and Technology. That was about computers and introduction to programming and some basic concepts. After that, I did a Bachelor of Information Technology, majoring in Information Systems. That didn't cover any hardware, but it was focused on more things like Unix, programming, and networks. During that course, I did cover things like binary numbers, zeros and ones, adding and subtracting binary numbers. And I do remember at the time wondering when I'd ever use binary numbers again. Turns out this year. Most of my career I've been doing systems administration work, which means I've been working on servers like Linux, virus, Windows, keeping those things running, and doing a lot of work in infrastructure. The last couple of years I moved into IT management, but I was recently laid off, picked up a contract, so if anyone knows of any management jobs going, let me know. A couple of years ago I saw the huge demand and interest in the Raspberry Pi. So I took note and decided I should know more about these things. I've been trying to figure out how to get started and how they work, and also came across the Arduino and some other things like the Deagle Line Black. But I saw an email to the Try and Beg mailing list just before this course from Pete Soper, so thank you Pete, about this edX course starting up. And that looked intriguing, so I thought I'd jump in. edX is what is known as a MOOC, a massive online open course. There are approximately 28,000 students who signed up for the class, but because they signed up, it doesn't actually mean they did any work. There were at least 4,000 students that purchased a real board and finished at least one lab. The board we used is a TIVA C-Series Waterpad Cortex M4 CPU in it. Pass that around. In the box there's also a Nokia 5110 display that was used, or going to be used for a game, but I didn't get time to finish that. ARM makes the CPU and Texas Instrument make the board. Both of them sponsor the course. This course was actually free, so you could do the whole course in simulation mode and not buy any hardware, not buy any software, and you would learn a lot.
TI makes the chip, right? They license the core from ARM.
I don't know. Didn't enter on the board, so I don't know.
Yeah, they license, it's the architectural definition that they license.
So with edX, there's an optional certificate that you can buy or pay for. So you go into like a verified course, and if you pass more than half of the labs on the real board, then you're entitled to a certificate. I decided that was worth doing. It was only $50, and I certainly got more than $50 worth of value out of the course. When the professors put this together, they were aiming for 3 groups. College students in the early in their career thinking about engineering. There were essentially have done a introduction to physics class and some programming. A group who likes like a bunch of techs who like gadgets, and if you're in that group, I recommend embedded.fm as a podcast. And then there's someone like me, a professional engineer, to learn more about embedded systems. The next 3 slides are course goals. I won't read them, I'll let you quickly peruse.
Was it just C or C++, C sharp, just straight C?
Just straight C. Since this was an online course, anyone in the world could do it. So the link at the bottom takes you to a page where they have 3 vendors they recommend: Alan 14, DigiKey, and Mouser. So if you clicked on those links, they took you to those vendors and preloaded your cart. So it made it easy to buy your stuff. The kit and board came in around $30. The optional LCD screen was about another 10, and there was also another optional component for wireless, which was an extra $20. So that's why there's a price range. Depends on what kits you bought. I ended up settling on buying my stuff from Element 14, but before I made my purchase, I did some research on Google looking for Arduino starter kits to try and find out what sort of things people do with Arduinos. After this course, I plan to learn more about the Arduinos and learn how to play with the different stepper motors and components. So I found a list of things that looked interesting, bought some stuff on eBay, realized that the shipping time could be a month, figured that I had enough time, so I bought some stuff on eBay, and I bought some stuff from Element 14. One thing with Element 14 that I learned is when you initially go there, you should sign in and register as a user. Because after you have your cart populated as a guest, when you sign in, your cart gets white.
Right.
And then you can stick components again.
Also, if you leave stuff in your cart for a few days, you come back, they'll send you emails like 15% off too.
No.
Yeah, so just a tip for Element 14.
Okay.
They hate it when you leave stuff in your cart.
And they're the ones that have the fulfillment center in South Carolina, right?
Yes.
It shows up
Gaffney.
next to
Gaffney.
It's very, very close. Yeah. For the stuff that's in stock, but watch out, some of their stock is in Great Britain.
Actually, speaking of in stock, I had a problem with Element 14. One of the parts that I needed was a RCA jack to plug headphones into. So that was in my kit, and I ordered it, and by the time I got ready to use that in my lab, I realized I didn't have it. So I went back to Element 14, realized it was still on back order, so I had to cancel that and buy it from DigiKey.
One thing about Element 14, that's why I buy all the Raspberry Pi stuff from. If you want to return something, I return a Model 2 only because I stupidly made a mistake. It was my fault, not theirs. They didn't question it. They said, fine. And they send me prepaid UPS label. So it doesn't cost me anything to send it back, even though it was my fault.
Very nice. So this is a picture of the board, and the breadboard next to it is actually from one of the labs. It's a finite state machine simulating a traffic simulator. Simulating traffic signals, red, light, green. Software that we use. So Kyle is a program developed by ARM and is free to use and free to compile. There's a limitation that your code cannot be larger than 32K. After that, you need to buy the professional version. All the stuff we did was well under that though.
Question, is that 32K for your code, or is it 32K for the entire, when it binds to the libraries, is it the
I
whole?
don't know, when you go into the debugger, it pops up a message saying limited to 32K. I'm not exactly sure
Okay,
about the definition.
It's probably the whole thing.
okay.
And is it operating system independent, or is it one of those Windows only?
Windows
Bummer.
and Mac.
Oh, okay.
So it doesn't run on Linux.
That's all virtual machine.
Yes, it does run on Windows and it runs in VirtualBox on Linux, because that's how I used it. So Kyle has a compiler, debugger, and simulator all built in. So you can actually write your code, compile it, and test it all in software. The professors wrote an extension to Kyle for grading simulation. They call it Texas. So that allowed you to write your code in Kyle, test it, debug it, and then when you're ready, you ran the grader software on it, and it will do the simulation on it for you and give you a grade. Everything we wrote was in C. Apparently C is popular in embedded. As you can imagine, 28,000 students, you're not going to get much time with a professor. So the support they had set up was Piazza, which is a bunch of student forums. Early on in the course, the professors encouraged study groups to be formed. They recommended find a bunch of people in your time zone and form a study group. I didn't bother because my time constraints wouldn't work, so I think a few students did. This is what Piazza looks like. Along the top, which you probably can't read, chapters. So the way this was structured is there was basically 14 or 15 chapters in a book, and each chapter you did each week. So when you needed help on like chapter 1 or chapter 2, you just click up here and it would organize the post by that chapter. That URL there is a copy of the work used, so that is also a free online resource. This is what the edX interface looks like. So it was a mixture of videos, text, and interactive demos. This is an example of a lab simulation. So when you wrote your code, you used the debugger and compiler and got the code working. After you got it working, you then ran another option inside Kyle, and that enabled Texas. From there, you then clicked on a grade button, and it then executed your code and gave you a grade. You may be able to read it, but up there there's a number called 5572. That's a random number generated for every student. So that was a unique number for me. So I then had to copy that number to the grade simulator and then do the grade again. And then that generated a hash that I had to copy back here. And then that was my grade. So that was one way to avoid, like even if I posted, hey, the score for this 5572 in a forum, probably wouldn't be of use to many people because the odds of them getting that number are pretty low.
How does it's grading the software that you wrote for that lab? Is that,
Yes.
And a lot of times there's multiple ways that you can write software to accomplish the task.
Yes.
How good was it at recognizing you got the right outcome independent of the path that you took to get there?
It was pretty good. There were some labs that I got 100% on, and then when I ran code on the real board, it dinged me on a few things. So, but overall it was pretty good.
So if I understand it, the simulator is kind of looking at the behavior right? So-
Yes.
Yeah, so it's detecting the fact that you're turning the LED on and you're detecting the switch and so on. So it's detecting the external behavior. I'm gonna guess
Right,
that
yeah.
it's
It's a
not
functional
looking-
observation.
It's not actually looking at the threads,
Yeah.
logic.
Because like when I took Code Academy, it would ding me sometimes because I went at it a different way than the code had expected. So I like that approach. I think that makes a lot more sense.
Yeah, like during simulation for like if you had to blink an LED, a little box pops up and shows you the LED blinking on and off.
So it's a functional, it's great.
Grading on the real board was similar, same technique. After you had it running in the simulator, you then uploaded your code to the board and then ran through a similar dance. This course was first run January 2014. One change they made to it this year is they added another lab, Lab 16, which is about Internet of Things. One thing I missed was during the introduction lesson, the professor had an unboxing video and he showed you how to connect the USB cable to the launch pad. And he talked about making a $13 mistake. So what he was talking about was if you press too hard when you connected the cable, you can snap the connector off. At that point, you buy another launch pad, which happens to cost $13. Sounds like he's done that a few times.
Or had students in that.
Always had, yeah, there was also notes that if you do happen to do that, here's some tips on how to solder it back together again. Didn't sound that much fun. Binary numbers are 0 or 1. You can get an 8-bit binary, a 16-bit binary, and that was all about adding them together, and that became useful when you had to program certain registers. You had to set certain things as a 1 or a 0 to make them function. This is a picture of an embedded system. This is an embedded system group. You've probably seen something like this before. So an embedded system has a microcontroller, processor, a RAM, ROM, and I/O ports. And they normally talk to the external world via I/O. I/O port can be either input or output. CPU registers are high-speed storage inside the processor. Assembly language was mentioned in one of the chapters, but at the start of it said you can skip over this if you want to because we're not doing much with assembly. With the launchpad, there are certain chunks of memory that are dedicated to certain functions, and there are gaps in between. When you write software, the first step is you write the code, you then compile it into an object code, and you then run that in the simulator or on the real board. This was an introduction to electric circuits. This is where high school physics would have been useful. So we talked about resistors, voltage, and current. But this was not about circuit design, so this wasn't used much.
You said high school physics, does that mean that junior high, this would be too up for junior high kids?
Well, this chapter was talking about resistors and having things in parallel and series, so not really, no. information is stored on a computer in binary form is usually stored in a transistor. Transistors that are made with metal oxide semiconductors are called a MOS. So a digital 0 on the Stellaris board is equivalent to a voltage between 0 and 1.3. A digital 1 is equivalent to a voltage of between 2 and 5. The gap in the middle is there to allow for high-speed transfers, and it's used for nothing. So as the bits flip from 0 to 1, if you happen to read something in the middle range, then it's ignored. And to find out what a 0 and 1 is on your particular board, you have to read your data sheet. Positive logic is the presence of voltage is called a 1 or true. Negative logic is the opposite of that. And it is important to know the difference because certain ports are different. I got tripped up a few times when I copied example code and reused it and found out that one was negative logic and one was positive logic, and the bits I was using need to be flipped. We covered logic functions. Logic functions. So this is AND and ORs and NOT ORs and XORs and all sorts of fun. You basically have to learn these sort of tables. This became useful when you had to set registers. So when you had to ensure a certain register was a 0, you could either AND it or OR it together, and you came out with a value that you're looking for. Module 5 was all about an introduction to C. They talked about the version of C we used was the original. The next version of C on from that was called C++ or C with objects. The version after that was called Professional C or C99.
Did you have experience programming prior to this?
Programming, yes, but not in C. So this was challenging. So in university I programmed in Pascal. So I knew the concepts and constructs, and I've written code before, and so I've done a little bit of programming and was comfortable with that, but knowing the syntax of C was new. And to help you with that, during the course, we had access to Zybox, which was also free. Zybox is a website with EPUB books on it. With EPUB books, you do some funny things, some fancy things like add code, compile things, you can drag and drop, and have animation, videos. So I spent a lot of time in this, learning how to program in C.
You said during the course you still have access to those?
No.
Bummer.
Yeah, no, it was just during the course they had it open, so I guess the sponsor has to pay for it.
Back up for a second. Yes.
On the board, there are different parts do different things, so pins are grouped in different sections. With an input port is read-only, and an output port is read-write on this particular board. A lot of the pins have alternate functions. So you initialize the pin and tell it at the time of the program when it starts up what you want to use it for. set some of these pins for alternate functions. To initialize an I/O port, you have to run through 7 steps. First, you have to activate the clock. If you forget to do that, your code crashes and doesn't work. And it gives you an error telling you that it's start the clock. For this particular example, port F0 was used, so you had to unlock the GPIO pins. This example was actually enabling port F bits 0 to 4, which are 3 LEDs and 2 switches. To do that, you have to write the hex values or binary numbers to actual registers to set. Since this example, digital was needed, analog was disabled, GPIO was turned on, and then in step 5, EF4 and 0 was set to be input ports, and the other 3 were set to be output. The alternate function was disabled since we wanted to use this for digital. Ports were enabled, and the last step was to actually enable them for digital writes and reads. So each port that you try to use, you have to do this initialization sequence. The professors talked about writing friendly software. So what they were meaning was, if you have a module that needs to use PF0, for example, and then you wouldn't use this sequence of code to initialize it because it turns on a bunch of other ports and registers. So if you did that and then you had a second module also running, they might collapse and override each other and cause all sorts of fun and games. It's very difficult to debug. So they stressed that you should only turn on the ports and pins that you actually need to use for your program.
And more importantly, not mess with bits associated with other pins.
Yes,
So you have to mask only the bits that you want to
yes,
mess with.
yes.
Question. Did that imply that there's an individual clock source for port F?
Yes.
Versus, so I'm gonna guess that allows for just exercising the piece of the chip that's, in other words, you're kind of enabling power to that port
Yes.
by running the clock on it. That's clever.
Yeah, these launch pad, all these TI chips are all about power. So each of the different banks, each of the different peripherals has a separate clock enabled that the data sheet we usually tell you can say, 10 milliamps if you set off this particular GPIO bank, and 20 milliamps if you shut off this UR bank. That sort of thing.
So when you're trying to debug an embedded controller, sometimes you don't have a screen. That makes it difficult. One way to find out what's going on is you can install an LED and then make it blink under certain conditions. Blinking LED is actually fairly low cost in terms of cycles to see a reaction. Some hardware debugging tools include a logic analyzer or an oscilloscope. A logic analyzer can analyze different channels and tell you what bits are coming out and of the board. An oscilloscope reads voltage versus time. So they have similar things, and some oscilloscopes have logic functions in it and vice versa.
Did the simulator have a built-in logic?
Yes. And that was useful.
Was the simulator was entirely part of the course, right? Not No, or was it the kill tool?
Simulator was part of Pilot. So, yeah, it was part of the software we're using. So when you try to debug stuff, you turn the logic analyzer on and you can specify, I want to see port F0 and see what it's doing. Make it put a watch on it. So you then see toggling working its magic.
Is Kyle something that you downloaded and installed in your Windows
Yes.
computer?
Yes.
And does it have the big honking GUI interface that's got 27 menus and 600 buttons? Or is it
Yeah, it's not that
relatively, so it's not terribly complex?
It's, well, the piece that I was using was fairly simple.
Quick question, did you have any experience with a TI program called Code Composer Studio?
No, I've heard of it and I've downloaded it for Linux, but I haven't installed it yet. But no, I haven't seen it.
Yeah, the reason I ask is that in my mind is an example of an extremely complex interface.
Okay.
I was just curious how straightforward Kyle is.
So you're running Linux, so you ran all this in a virtual machine,
Yes.
no problem?
That's fine.
In Windows?
The Windows virtual machine, yeah.
Yeah. Yeah, on your Linux, you put in VirtualBox and it ran through there, okay.
So although I will say on this one, this is Ubuntu 14, and I tried for a couple of hours on Saturday to try and make this one work, and I couldn't get it going, so I can't do any live demos today. My one at home is Ubuntu 12, and that just worked.
So, what did they expect for hours a week they thought you should work on this? I mean, I was at a MIT Parents Weekend a couple of years ago, and they were talking all about this great interactive online teach yourself how to write code class, and they said, oh, it only requires, 8 or 10 hours a week of your time, and it's free, and it's online, and I'm like, nope, that won't happen. So did they have any expectation?
They had estimates, so it depended on how far you were going to go with it. I saw some numbers in the 10 to 15 hour range, but for me, I spent more than 20 hours most weeks.
Yeah.
Each week I spent more than 20 hours on it.
But when you got done, your skill level had been
Oh,
taken.
huge, yeah.
So if you're gonna take the course over again, how many hours are you gonna spend?
Well, I've got the code written for the first 14, so
Well, yeah, you can take different,
not much on that now, but
similar in level, but different examples.
what, with my skill level doing a similar course,
Yeah.
Questions why? Why would you?
probably
You understand the reason for the
still
question?
be fairly significant because the labs took a lot of time. So some of the labs were straightforward that had examples in the text, and then the lab was very similar. So that was a quick fix once you figured out, just tweak these couple of things and you're done. But there was one lab, like later on, I talked about a digital to analog controller. The book had a 3-bit version, and the lab you needed to build a 4-bit version. How hard can that be? That was easily 10 hours plus getting that thing working. So things like that just completely trip me up. So I don't know.
Okay. So it sounds like a big portion of your time is actual hands-on debugging and
Right.
that kind of stuff. And so,
Right. So the videos and text was fairly straightforward to read through. There's a thing called Systic that tripped me up, that you had to fiddle, so Systic is a timer, and you have to fiddle with the timer to make things slightly different. So when you're generating sound waves, you have to change Systic, put certain values to make it wind down a little bit faster, a little bit slower, depending on how fast you wanted your periodic interrupts. So that took a while to get my head wrapped around how Systic actually functioned and what these matching numbers needed to be. So once I understood what that formula was, and was able to set the controller properly, then it was very straightforward. But learning that concept took a while. So some things in here certainly tripped me up, and the next time around it'll be a lot faster.
This apparently is not for somebody who's only got 3-5 hours a week to,
No. No. Way more than that.
I mean, in many ways, it's a genuine university level course, isn't it?
Yes.
It's University of Texas.
Right. It's from the university, and it's an introduction to embedded systems course at that level, yes.
Is there an option to extend out the end of the course and stretch it out to give it over more time, or is it, you're just stuck for that time?
No, the course is bound, so it's open from that time to the end time. I have access to the materials, and I can still see the videos and play with the labs. I just won't get any grades for it.
Right. So you could audit the course for like one semester and then do the next semester as well?
Sure. Well, you can read that textbook right now.
Yeah.
I think with the edX stuff, you can actually, like any of us can go in right now and sign up for the course today and have access to the materials today. We won't have access to the grades and stuff. This is how it worked last year when they ran the same course.
Okay.
I don't know if that's true now.
Yeah, I don't know. I've still got access to the edX interface, but the grading stuff is useless. So yeah, I don't know what would happen if you signed up for it right now.
Is it just offered each spring? Is it annually?
It was January last year was the only other time they've done it.
Okay.
So based on that, I assume January next year they won't do it again.
16 weeks, 12 weeks.
It's closer to 16, yeah. So in the product life cycle, there's a series of stages. You start out gathering requirements, figuring out what you want to do. You analyze the problem, then you move on to design, then you do some development, test it, deploy it, see how it works, and then you might do another revision, and then you start the cycle again.